Hello everyone. Today we are going to talk about mechanisms of breathing. When we inhale the air is going to enter into our nasal cavity or into our mouth, but breathing through our nose is way better than breathing through our mouth. So after the air enters into the nose or the mouth, it's going to enter into the pharynx. From there, it's going to travel into our larynx, which is our voice box, and then into our windpipe, which is our trachea. And then the trachea is going to start branching out into the bronchi branches, and from there, it's going to enter into the lungs until it reaches the alveoli. And this is where the gas exchange is going to take place within our lungs. Before the air enters our lungs, it's going to get warmed up so that actually the alveoli are not going to be destroyed or damaged by the cold air. The air is also going to be humidified. So the air reaches 100% humidity before it reaches our lungs, and it's also going to be filtered so that again we trap dust particles, pathogens, etc. We filter them before the air reaches your lungs. Now, um, there are muscles that are going to help us with the process of inhaling and exhaling. So we've got our intercostal muscles, we've got our sternocleidomastoid, even your abdominal muscles are going to help you, especially when you are forcing yourself to exhale more. So if you force yourself to exhale a lot of air, you will notice that your abdominal muscles tenses up because they are going to help you push that air out of your lungs. Also, our diaphragm muscle is definitely pretty important. So when we inhale the air, the diaphragm muscle contracts and it moves downwards so that it can give your lungs room to expand. When we exhale, the diaphragm muscle is going to relax and it's going to push itself back up. Our lungs are surrounded by a pleural sac. If we look at this image and we look at this air-filled balloon, which is going to represent our lung, and then we have another balloon right here. This is going to represent our pleural sac. So this balloon right here, which is representing our pleural sac, you can see that there is fluid inside of it. And you can see that this balloon is only made up of one membrane, but when it wraps itself around the lung, you will notice that it kind of looks like it has two layers. So if this is our lung right here, this part of the pleural sac that's closest to the lung is going to be known as the visceral pleural layer. And then the outer layer right here, which is going to be the one closest to the thoracic wall, this one is going to be the parietal pleural layer. In between the two layers, you're going to have a cavity, and that cavity is going to be filled with fluid. That pleural fluid is important because it's going to act as a slippery fluid that's going to prevent those two pleural membranes from rubbing against each other, especially because your lungs are inflating and deflating all the time. And so with inflation and deflation, without any fluid in there, those two membranes are going to start rubbing against each other, and that's definitely going to be painful. Also, that fluid in there is pretty important because it's going to kind of create like a vacuum effect, and it's going to help push your lungs tight against the thoracic wall. If your lungs are not pushed tight against the thoracic wall, your lungs are going to collapse. Now, the pressure inside right here, So the pressure in between the two pleura layers, we refer to it as the intrapleural pressure. And the intrapleural pressure is always lower compared to the atmospheric pressure. It's about 3 degrees lower compared to the atmospheric pressure. If that pressure increases, so if that pressure becomes, let's say, equal to your atmospheric pressure, that would be disastrous because then your lungs will collapse. If the intrapleural pressure becomes higher compared to the atmospheric pressure, same thing, disaster, because that would cause your lungs to collapse. So to prevent your lungs from collapsing, that intrapleural pressure always has to be lower compared to the atmospheric pressure. Our trachea and our bronchi are lined with ciliated epithelium tissue. And you can see the cilia right here on the apical surface of our epithelial tissue. The cilia are bathed in a watery saline layer. And above that watery saline layer, there is a sticky layer of mucus, and that sticky layer of mucus is going to help trap most of the inhaled particles before it reaches your lungs. The cilia are going to sway back and forth with an upward motion so that they can move the mucus towards the pharynx. So if we have cilia right here, then our trachea, the cilia is going to keep pushing those particles in an upward motion until it reaches your pharynx, which is your throat. Once it reaches your pharynx, we are either going to spit it out or we are going to swallow those inhaled particles. And if we swallow it, it's going to go into your stomach, and the condition there is highly acidic. So the high acidity within your stomach is going to break down those particles. That watery saline layer is actually very important for the cilia movement. Without that watery saline layer, the cilia is actually going to get trapped in the mucus and it's not going to be able to move. And so if that happens, the bacteria is actually going to start to reproduce and increase in number because they're trapped and you're having such a hard time actually moving them. So the bacteria kind of starts to multiply, and that can cause lung infections. When we inhale, the air is going to enter into our larynx, then into our trachea, and you can see that the trachea starts to branch out. The more it branches out inside of our lungs, the more those branches get smaller and smaller until those branches connect to a bunch of alveoli. This is where the gas exchange is going to take place. So if we zoom in, we have one alveolar sac right here, which is made up of a bunch of alveoli. There's going to be a bunch of capillaries on top of our alveoli. Um, so any oxygen that's going to be within your alveoli, so after you inhale and the oxygen enters into your alveoli and the alveoli are going to get inflated with all of that oxygen, the oxygen is going to leave your alveoli and enter into your capillaries so that it can be moved into your bloodstream. Your capillaries are also carrying carbon dioxide. So the carbon dioxide in your capillaries will exit the capillaries, enter into your alveoli so that we can exhale it out. So as you can see, the oxygen and the carbon dioxide gases are going to easily be transported into and out of your alveoli, and so that's why we say this is where the gas exchange is going to take place. And the reason why the gas exchange is going to take place pretty fast within our alveoli, that's because our alveoli, it's very thin. It's lined with simple squamous epithelium tissue, and your type 1 alveolar cells are the ones that kind of make up the walls of our alveoli. We also have type 2 alveolar cells, and those produce what's known as a surfactant. And the surfactant, consistency-wise, it's kind of like soap detergent that's going to be coating the inside of your alveoli. The surfactant is actually pretty important in preventing your alveoli from collapsing, because if your alveoli collapse, then your lungs are going to collapse. Um, so to explain how the surfactant works, if we zoom in on one of the alveoli, so singular, we refer to it as alveolus. So let's say that this is one alveolus right here. Lining the inside of the alveolus, we actually have a layer of water. And then, of course, the inside of the alveolus, this is where you're going to have the air. So if we zoom in on the water molecules right here, so here are a bunch of water molecules. Now the water molecules are known to bind to each other via a bunch of hydrogen bonds. So if we look at this middle water molecule right here, notice how this water molecule in the middle is basically binding to all of the water molecules that surround it. So you can see that it's binding right here to this water molecule right there, and up and down. And you can see that this middle water molecule right here, um, those vectors that are presented right here, they're all going to cancel each other out. So the one on the right and the one on the left equal forces, so it's going to cancel out up and that top one and that bottom one, again, equal forces, they're going to cancel out. But if we go ahead and look at this water molecule right here, you can see that this water molecule, it's going to bind to the water molecule on both sides, on the right and on the left, and it's going to bind to the water molecules on the bottom. But it's not going to bind to any water molecules on the top, because above that water molecule, we have air. So what's going to happen is that the right and left forces right here, those are going to cancel each other out. But then notice how this force that's going downwards, there is no force that kind of equalizes it on the top. And so what happens is that since those are going to cancel out, all the force is actually going to be headed downwards. And that creates what's known as a surface tension. So the force is going to be too powerful, kind of pushing that water molecule downwards, creating a surface tension up at the surface right here. So all of these top water molecules, they are actually going to be pushing downwards, because again, there is no upward force to kind of equalize it. And so that's what creates the surface tension. That's why when you look at the surface of the water and you wonder why some insects are actually able to walk on the surface of the water, because they are very light, those insects, and they are not breaking that surface tension. So what happens is we end up with surface tension within our alveolus. Now that surface tension, as I said, is going to keep pushing downwards, and it's actually going to cause the alveolus to start collapsing. And so what happens is to prevent the collapse of our alveoli due to that surface tension of the water within our alveolus, type 2 alveolar cells produce a surfactant. And the surfactant, what it's going to do is it's actually going to that surfactant, that kind of like detergent like substance, is actually going to come and break that surface tension, because that surfactant is going to start as you can see, like those purple circles that I'm drawing, it's actually going to kind of push itself between the water molecules, and it's actually going to break that surface tension. And so when that surface tension is broken, the alveoli are not going to collapse. Now, when do we produce that surfactant? We produce that surfactant by the 34th week of pregnancy. And so that's why if babies are born premature, and they have not produced their surfactant yet, what's going to happen is their lungs are going to collapse. And so therefore premature babies are going to have to get hooked up to ventilators because they are not producing their own surfactant yet. And so another thing they could do is, other than hooking them up to ventilators, now they have like surfactant they actually spray. Again, to prevent those premature babies from having collapsed lungs. And so the surfactant, what it does is it lowers the surface tension within your alveolus, preventing your alveolus from collapsing. The relationship between pressure and volume is inversely proportional. So Boyle's law is basically explaining that inverse proportional relationship between pressure and volume. That means that as the pressure increases, the volume is going to decrease. And as the pressure decreases, basically the volume increases. So you kind of explain that. Let's say that you have this beaker right here, and you have some particles within that beaker. And so you can see that the volume here, it's pretty large, and so the pressure inside of that beaker is not going to be high, because those particles are not going to be bombarding against each other or bombarding against the walls, because they actually have room to move. But what happens is, if we go ahead and start decreasing the volume within that beaker, so notice how the volume decreased, now there isn't enough room for those particles to move, and so they're going to start bombarding against each other, they're going to start bombarding against the walls of the beaker, and so the pressure in here is actually going to start rising. So you can see that as the volume decreased, the pressure increased. And so that's, again, Boyle's law. Now, Dalton's law is basically explaining the partial pressure of a gas. So when we think of air, air is made up of a mixture of gases. So like oxygen gas, nitrogen gas, etc., they're all mixed in together. Now, if you want to actually calculate the partial pressure of a certain gas, what you do is take the whole entire atmospheric pressure, which is around 760 millimeters mercury. That's the unit that we use for gas pressure, and you multiply that atmospheric pressure by the percentage of the gas in the atmosphere. So let's say that I want to figure out the partial pressure of the oxygen gas in the air. So I take my atmospheric pressure, which is 760, and I multiply it by how much oxygen do I have. So if I say that the percentage of oxygen in the atmosphere is around 21%, you multiply that by 760, and so that would tell you that the pressure of the oxygen in the atmosphere is around 160 millimeters mercury. So Dalton's law is basically a way to calculate the partial pressure of gases in the atmosphere. We also have to account, though, if the atmosphere has water vapor. So if basically the air is humid, which means there is water, you have to take that into account and you have to subtract the pressure of water. So let's say that your air is pretty humid and so it has water. You have to subtract the pressure of water from the atmospheric pressure so that you can calculate that partial pressure of a certain gas. So if the atmospheric pressure, one more time, is 760, and let's say that the pressure of the water is 24 millimeters mercury, again, this is going to be given. So let's say they tell you that the air it's 100% humid and the pressure of the water is around 24. You have to subtract that 24 from the atmospheric pressure, and then you multiply that by the partial pressure of the gas that you are trying to calculate. And so the partial pressure of oxygen in dry air is around 160. But notice how the partial pressure of oxygen in humid air, it's 155. And the reason why it's less, because we had to subtract out the pressure of water. So that's Dalton's law. It helps you figure out the partial pressure of gases. Now, if we look at this image right here, we are going to talk about our lung volumes and capacities. So we have what's known as the tidal volume. That's basically around 500 mils for both females and males, and that's the amount of air that we normally inhale and we normally exhale without putting any extra force. So right here, when you inhale, you can see that the volume inside of your lungs, it's going to increase because you're intaking air. And so that upward wave is going to represent inhalation. And then as we go downwards, that's going to represent exhaling. So we normally inhale about 500 mils of air and we normally exhale around 500 mils of air. And that's usually traced and using what's known as a spirometer. And now we have digital actually spirometers that can easily calculate those volumes for us. Now, if you force yourself, let's say that you already inhaled the 500 mils of air, right? So you took the normal breath, but then you went ahead and you forced yourself to even inhale even more air. That's going to be known as the IRV, or the inspiratory reserve volume. And it differs between males and females. You're going to notice that males, they will have actually larger lung capacities. They're able to intake more air compared to females. Now, if you force yourself to exhale more air out, that's going to be known as the expiratory reserve volume. Now, even if you force yourself to exhale and you feel like that's it. I can't exhale anymore. Does that mean you've exhaled all the air out of your lung? No. You actually still have some air inside of your lung, and we refer to it as the residual volume. So the residual volume is not going to be exhaled out. Actually, we don't want to exhale the residual volume because otherwise your lungs are going to collapse. So there's always a bit of air within your lungs, known as the residual volume, to prevent your lungs from collapsing. Now, capacities are basically where you add a bunch of volumes together. So your total lung capacity, if I want to figure out, my total amount of air that my lungs can actually intake and exhale out, I would basically take my tidal volume and I would add my inspiratory reserve volume, my expiratory reserve volume, and my residual volume. So that's going to be my total lung capacity. Your vital capacity is basically everything except your residual volume. So it's your tidal volume plus your IRV plus your ERV. That would be your vital capacity. And as you can see, the tidal volume for both females and males, it's about the same, but then the IRV and the ERV are going to be different, and so therefore the lung capacities are also going to differ between males and females. If we look at those three graphs right here, this bottom graph is representing the volume of air inside of our lungs. This middle graph right here is representing the pressure, the intrapleural pressure, which is the pressure between the visceral and parietal pleural layers. And then this top graph is representing the alveolar pressure, so the pressure inside of our lungs within our alveoli. If we take a look right here at the alveolar pressure, we said that the atmospheric pressure, so the pressure of the air, is around 760 millimeters mercury. But to simplify things, we are going to say that the atmospheric pressure is 0. And you can see right here, the 0 is going to represent the atmospheric pressure, and then you can see if the pressure increases, we are going to represent it by a positive pressure, and then if the pressure decreases below the atmospheric pressure, we are going to represent it by negative numbers. So if we take a look right here at time 0, you can see that there is no flow of air. So you can see right here, the volume within your lungs, it's not changing. You can also see that the pressure in your intrapleural region, it's -3. Again, just that just means that the pressure there is below your atmospheric pressure by around 3 points. So that's why we are representing it by -3. And then you can see that the alveolar pressure is at 0. So the thing is, when your alveolar pressure is equal to the atmospheric pressure, as you can see right here, they're both at 0, no air is going to flow. So no air is going to enter your lung, no air is going to exit your lung. There is absolutely no airflow when the atmospheric and the alveolar pressure are equal. And you can see that at all times, the intrapleural pressure must always be below your atmospheric pressure. Otherwise, your lung is going to collapse. So if we look right here at time 0 to 2 seconds when we are inhaling, our muscles are going to start to contract, like your diaphragm muscle, your intercostal, etc. and you will notice that your thoracic volume starts to increase. So we are starting to inhale, so you notice that the volume is increasing within your lungs. If you remember Boyle's Law, we said that the pressure and volume are inversely proportional. So as the volume increases, you will notice that your alveolar pressure is going to decrease, and you can see that it's decreasing beyond the atmospheric pressure. Your intrapleural pressure is also going to decrease as well. So as the pressure starts to decrease, the air is going to move from high pressure to low pressure. So if the pressure inside of your lungs, it's now below the atmospheric pressure, the pressure in your atmosphere is now higher. That's why the air is going to move into your lungs. So when we inhale, the reason why when we inhale the air moves into your lungs, because now the pressure inside of your lungs is lower compared to the atmospheric pressure. As the air starts to flow into your lungs, the pressure eventually is going to start to increase. So you can see right here, the pressure actually starts to increase until your thoracic cage stops expanding. And when the pressure, as you can see, starts to increase within your lungs and it reaches one more time to 0, meaning that now it's equal to your atmospheric pressure, no more airflow. So you can see right here, the air is not flowing anymore. And then at the end of inspiration, our muscles are going to start to relax, and your diaphragm also starts to relax and return back to its relaxed position. And then we move into the expiration stage, so kind of like right here, from 2 to 4 seconds, we are going to be exhaling. And so you can see that as we exhale, the volume within our lungs starts to decrease because we are pushing all of that air out of our lungs. And then, as we said, as the volume decreases, the pressure is going to further increase within our alveoli. And so, as we said one more time, air moves from high pressure to low pressure. So when you are exhaling and your alveolar pressure increases above the atmospheric pressure, so you can see right here, it's above the atmospheric pressure, the air is going to be pushed out of your lungs from high pressure to low pressure. And then you can see right here your intrapleural pressure, even though it's increasing, you notice that it's still below your atmospheric pressure. So the intrapleural pressure always has to be subatmospheric, meaning that it always has to be below the atmospheric pressure, otherwise your lungs are going to collapse. And then you can see that the cycle is basically going to keep repeating itself. And whenever the pressure of your alveoli is equal to the atmospheric pressure, basically no air is going to flow either in or out of your lungs. This image right here is showing you that there's always a cohesive force within your intrapleural fluid, causing your lung to adhere to the thoracic cage. And that's important because if your lung is not adhered to the thoracic cage, the lung is going to collapse. And there's a combination, a constant combination of an outward pull by your thoracic cage and an inward pull by your lungs trying to kind of recoil back to their original shape, and that kind of creates a subatmospheric pressure right here within your intrapleural fluid. That's why, as we said, that pressure, when we looked at the previous image, it's around 3 degrees lower compared to the atmospheric pressure. And we said that it always has to stay below the atmospheric pressure. What happens if someone, let's say, gets shot, or one of your ribs actually cracked and pierced your pleural fluid, or if someone, as I said, gets stabbed, for example, and now you've kind of pierced that pleural fluid. What happens is air is going to start entering into that space, into that intrapleural space. And what happens is when air enters into that intrapleural space, the pressure within your intrapleural space is actually going to start to increase. And so when the pressure increases, your lung is not actually going to be stretched anymore towards your thoracic cage. And as you can see, the lung kind of starts to pull away from the thoracic cage. And what happens when the lung kind of pulls itself away, the lung is going to collapse. And we refer to that as pneumothorax.